Hello everyone. In this video, I will be discussing about valence bond theory in coordination compound. Okay. Werner theory was successful in explaining various types of valencies like primary valency and secondary valency in coordination compound. Werner theory was successful in explaining that why certain groups attached to the metals are ionizable whereas certain other groups are non-ionizable. But as there was development in chemistry, it was found that certain compounds like COF6 3-, it has certain magnetic moment, while CONS3 6 3+, it is coordination compound of cobalt, does not have any magnetic moment. It has mu equals to 0 and both have octahedral geometry. So it was found that Werner theory cannot explain this observation. Werner theory was not applicable to the observation of magnetic behavior. Therefore, a new theory, valence bond theory, was applied on coordination compounds. And valence bond theory in coordination compounds takes place in 3 steps. So, okay, let's see what are those steps. First one is that central metal ion provides as many as vacant d, p and s orbitals, which is equal to its coordination number. Okay. These vacant d, p and s orbital hybridize together to produce equal number of hybrid orbitals, which are equivalent energetically, symmetrically, chemically and stereochemically. You must have learnt in the hybridization topic that the hybrid orbitals are equivalent to each other. Similarly, here also the hybrid orbitals which are produced are equivalent energetically, symmetrically, chemically and stereochemically. Now third, ligands provides a pair of electron to each hybrid orbitals, forming a special type of covalent bond that is called coordinate covalent bond. So you have to remember one thing here is, you have to note it down that the bond formed here is coordinate covalent bond. Okay. And next, it also involves slight charge separation, and this ionic character is also added to stability of complex. Okay, we will discuss it that how there is certain charge separation, what is the role of that. Before moving further, now I will take these two compounds and explain that what happens that COF6 3- does not have has certain magnetic moment, whereas CONS3 6 3+ does not have any magnetic moment. How valence bond theory was applied to explain this observation. Okay, note it down fast. We have already discussed that shape is directly dependent on the coordination number of the compound, coordination compound. So here we can see that if the coordination number is 4, then its hybridization is sp3 and its shape is tetrahedral. Similarly, coordination number 4, hybridization can be dsp2 and at that time shape becomes square planar. Okay. Similarly for 6, there can be 2 different hybridization, d2sp3 or sp3d2, and shape in both cases octahedral. Only hybridization differs. Okay, fine. Now we have to find that under what circumstances for coordination number 4, sp3 or dsp2 hybridization will take place, or in coordination number 6 we have to understand that in what condition d2sp3 hybridization will take place and in what condition sp3d2 hybridization will take place. But before moving further, please note down this because it is very important. Here you can see that shape is tetrahedral, square planar, octahedral. Note down the shapes because these are very important. So now I will discuss the hybridization of CONS3 whole 6 3+. Okay, but before moving further, it was found that in case of CONS3 6 3+, the magnetic moment mu equals to 0. It can be measured in the instrument called magnetometer. So it was measured to be 0. Now VBT will explain that how this magnetic moment becomes 0 in this complex. Okay, but before that we have to understand one thing, that how magnetic moment is calculated. So calculation of magnetic moment. Okay, so magnetic moment mu is equal to root under n into n plus 2. Okay, now where n is number of unpaired electrons. Okay, so if magnetic moment of this compound is 0, what can be concluded? That it has no unpaired electron. We can conclude this. Fine. So note it down, and now I will move on to finding the hybridization of this compound. Let's see. Now we can see here that coordination number is, its coordination number is 6. So what can be concluded? That the hybridization can be either, now two hybridizations are possible. I have discussed that in case of 6 coordination number, hybridization possible is D2sp3 or sp3d2. Okay, now we will see that what is the hybridization. Now what is the hybridization of CuNH3 3 plus cation, or this complex cation. Okay, but before this we have to keep in mind that its magnetic moment is 0 and it has no unpaired electron. If there would have been some unpaired electron, then it must have some net magnetic moment. Okay, so let us see. Now in this complex, cobalt electronic configuration I am writing, it's argon 3d7 4s2 4p0 4d0. Fine, you can see here. Now here cobalt exists because NH3 does not have any charge, so cobalt exists as CO3 plus, and its electronic configuration is of cobalt 3 plus is argon, remove 2 electrons from here, this 0, this 0, 2 electrons means it becomes also 0, and we have to remove one more electron to make it 3 plus, so it becomes 3d6. Now see, I am drawing these outermost electrons, outermost orbitals, 3d, 4s, 4p and 4d. Fine. So here you can see. Now fill the electrons. In case of 3d, there are 6 electrons. So 1, 2, 3, 4, 5 and 6. Fine. It has 0 electrons. It has 0 electrons. Now see here. For hybridization, if we take 1s orbital, 3p orbital and 2d orbitals, the hybridization becomes sp3d2. But in that case, there will remain 4 unpaired electrons. And if there are unpaired electrons, can its magnetic moment be 0? Definitely no. So we have to keep in mind that there are no unpaired electrons left. So when ammonia approaches, then pairing starts. Pairing starts, and the 3d electrons are paired up. 3D, 4S, 4P. Fine. Now, remember one more thing, that now the hybridization becomes what will be its hybridization? Here you can see that ammonia forms coordinate bond by donating its lone pair of electrons. So here 1 NH3, here 1 NH3, and all these electrons will be paired. 1 NH3, 1 NH3, again 1 NH3, 1 NH3. Okay, so hybridization becomes D2 sp3, and its shape will be cobalt, ammonia, 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 and here also one more ammonia. Its shape will be octahedral. So now we have to keep in mind that some ligands like ammonia can cause pairing, and we will see when I will tell you that further what are the characteristics according to VBT which are responsible for this kind of pairing. Okay, because and why pairing happens, it can be concluded from the fact that our ultimate aim is to achieve mu equals to 0. If there would have been some value of mu, then there would have been no pairing. Okay, fine. So keep it in mind and note it down further. Fast. So now I will take one more coordination compound, and that is cobalt F6 3 minus. Okay, in this compound there was some net magnetic moment, and we can say that mu is not equal to 0. And what does it means? That there are still some unpaired electrons present in the compound. Okay, and now you can guess that how it would happen. Now let us see again electronic configuration of cobalt is again argon 3d7 4s2 4p0 4d0. Here if we find out the oxidation state, then we can see that cobalt exists as CO3 plus. So electronic configuration of CO3 plus, again it's the same, argon 3d6 4s0 4p0 4d0. Fine. Now I will draw the outermost. See, this is 3d, this is 4s, this is 4p, and this is 4t. Now fill the electrons 3, 4, 5, 6. It is empty, and all these are empty. Now, because there is some net magnetic moment, so definitely pairing will not take place. So some electrons will remain unpaired, and in this case, hybridization becomes there is no role of this 3D, and hybridization becomes sp3d2, because here there is no space empty for two electrons, because remember one thing, that the ligand here comes as F minus and it forms coordinate bond, and in order to form coordinate bond, two electrons must be donated by the same atom, and in that case there should be a completely empty orbital, because in an orbital there can exist only two electrons. Okay, so here hybridization is now F, 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 F. So hybridization is sp3d2, and its shape again becomes octahedral, that is CO, F, F. Fine. So by this way you have to represent the shape, hybridization. And it was found that what will be its magnetic moment? Mu equal to root under n into n plus 2 Bohr magneton. This is called spin only magnetic moment, and its value is 1, 2, 3, 4. Here we can see that there are 4 unpaired electrons. Okay, so its value becomes 4 into 6 Bohr magneton, that is equal to root 24 Bohr magneton. And one more thing is that you will, when it was measured by using magnetometer, then it was also found that this value is, this calculated value is very close to the experimental value, is very close to the observed value. Okay, so we can say that this concept of valence bond theory to determine the magnetic moment is correct. Okay, but from here you have to remember one thing, that if pairing occurs, in that case we will use the 3d orbital of 3d orbital, but if pairing does not occur, then we will use 4d orbitals. Or in common, or in simple way, we can say that if pairing occurs, then there will be n-1 d orbital involved in hybridization, and if pairing does not occur, then there will be nth d orbital involved in the hybridization. Okay, note it down fast. So now, till now we have learned that in case of CuNH363+, magnetic moment is 0, and therefore its hybridization is D2sp3, because pairing takes place. Now, in this type of complex, n-1 D2NS NP3 orbitals are involved in hybridization. So you can see that n-1 D2. Okay, such type of complexes are called inner orbital complexes, because inner d electrons are involved. You can see here inner d electrons are involved. Similarly, they are also called low spin complex because they involve back pairing of electrons. We have seen earlier in hybridization that in case of when the ammonia comes towards metal, the electrons of cobalt pairs. Now spin paired complex, they are also called spin paired complex because resulting complex have spin pair configuration of electrons. Okay, all the electrons are present in pairs. So one is plus half and another is minus half. Both the electrons, both the type of pairing is present in it. They are also called hypoligated complexes because they are formed in presence of ligands in which donor is associated with low electronegativity and polarizability. Now we have to understand this term. They are called hypoligated complexes because the donor atom which comes to form chemical bond, coordinate bond, is having low electronegativity and high polarizability. So now when the ligand approaches the metal, because of its low electronegativity, it donates its electron very easily, and when the electrons are donated easily, they causes pairing of the electrons of d orbitals of metals, and hence the electrons present in the d orbital of metals are paired. This may be because of electron-electron repulsion. Fine. So what kind of ligands are able to cause pairing up? Ligands having S donor, P donor, C donor or N donor. N donor only in case of sp3 hybridization, because nitrogen can be sp2, sp hybridized as well, and in that case electronegativity increases as the S character increases. So if ammonia is there, then the electronegativity of nitrogen is not that much high, so it can donate its electron very easily. Fine. So you can note it down, and before that we will discuss. In case of COF6 magnetic moment is not equal to 0. So it was found that its hybridization is sp3d2 because there was no pairing taking place, and this type of complex is called NS NP3 ND2 type of complex. It is also called outer orbital complex because it involves the outer d orbitals during the hybridization. It is also called high spin complex because there is no pairing which takes place during the formation of complex, and hence there are always some unpaired electrons present which are responsible for the magnetic moment. It is also called spin-free complex because some of the electrons will always be present without their spin pairs. Okay, so it is always called spin-free complex. And this type of complex is also called hyperligated complex, and it is formed by the ligands which have high electronegativity and low polarizability, because these ligands do not donate their electrons easily, and thus they are not responsible for pairing up. They are not much able to apply that force or that repulsion which will cause pairing of the electrons present in the d orbital of metals. These ligands are halogens as donor, O donor or N donor. N donor in case of sp2 and sp hybridization, because with the increase in S character, electronegativity increases. So if nitrogen is present in sp3 hybridization, then it will be responsible for pairing, as here we have already seen in the case of ammonia. But if nitrogen present in sp2 or sp hybridized, then it will not cause pairing. So these are the terms which you have to remember. These are very important terms because in examination there can be a question: what is, write the difference between inner orbital complex, outer orbital complex, write the difference between low spin complex, high spin complex, write the difference between spin paired complex or spin free complex, write the difference between hypoligated complex and hyperligated complex, or sometimes they may even ask the individual terms. Okay, but you have to remember the reason why pairing took place. Okay, and the reason given by concept of valence bond theory. Some people may confuse, may write when it is asked that what was responsible for pairing in case of hypoligated complex. Then some students get confused and they talk about the spectrochemical series, which is not the part of valence bond theory. Okay, so you have to keep it in mind. Find that which theory in the examination they are asking about. Fine, note it down fast. And now we will discuss some hybridization involving coordination number 4. Okay, note it down fast. So now I will discuss hybridization involving coordination number 4, and for that I will take two examples, NiCl4 2- and NiCN4 2-. We have already discussed that where chlorine, because it is a very electronegative atom, will not cause pairing and the molecule will not involve inner d orbital for hybridization. Where in case of NiCN4, carbon is present as donor atom and carbon is not that much electronegative, so definitely it will cause pairing. Okay, fine. So now let us see about hybridization in NiCl4 2- complex. Here you can see that nickel exists as Ni2+, and in Ni2+, its electronic configuration is argon 3d8 4s0 4p0. Fine. If I draw it in orbital form, fine, see here, 1 2 3 4 5 6 7 8. So 3d 4s 4p. Because chlorine is not able to cause pairing, so these electrons will remain unpaired, and in case of hybridization, these two will come 4s and 4p will come, and hybridization becomes sp3. Fine. Whereas this remains as it is. Fine. So chlorine donates its electrons to form coordinate bond chlorine, 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 and chlorine. So its hybridization is sp3 and shape is for sp3 hybridization, shape is tetrahedral. Okay, fine. In examination, sometimes question comes that all the tetrahedral complexes are associated with high spin, and the reason for that is, in case of tetrahedral complex, you have to note it down. In case of tetrahedral complexes, there is no involvement of inner d orbitals, so there is no pairing up, so there is no change in the magnetic moment, and therefore these tetrahedral complexes are high spin complexes. Fine. Now we will discuss about NiCN4 2-. Similarly, here also nickel exists as Ni2+ ion, so its electronic configuration here also is argon 3d8 4s0 4p0. Again, if I draw it here, 3d8 1 2 3 4 5 6 7 8 4s and 4p. Fine. So now, if, because Cn is a ligand which has donor atom as carbon and it is not that much electronegative, so it will cause pairing, and after pairing Ni2+ becomes so for hybridization, this is 3d, this is 4s, this is 4p. They come together and cyanide donates electrons and forms coordinate bond. So hybridization is DsP2, fine, and its shape is nickel Cn 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 Cl 2 minus, and this shape is called square planar. Okay, so you have to note it down. Similarly, we can find out hybridization of various molecules according to valence bond theory. Fine. Now in examination sometime question comes that all the square planar complexes are associated with low spin. So now I think you can tell the answer that this is because in case of square planar, inner d orbital is involved and pairing is involved. So pairing reduces the magnetic moment, and so square planar complexes are always associated with low spin. Fine. Note it down both the concepts for coordination number 4. Fine. Remember one thing, I have already told that what are the factors, how you can decide in valence bond theory that whether a given ligand will cause pairing or not. We have already discussed when I discussed hypoligated complex and hyperligated complex. Don't go with spectrochemical series for deciding pairing in case of valence bond theory. Okay, fine. Note it down fast. So now, here are some questions which may come in your examination, and these are very important. So let us see. MnBr4 minus 2, MnCN6 minus 2, MnH2O5 whole 3 plus, FeCl6 minus 3, COH2O6 3 plus. Classify them as low spin and high spin complex. And I have already mentioned while discussing the hypoligated and hyperligated complexes. Okay, so we can use that concept and classify these coordination compounds as high spin or low spin complex. So Br bromine is an electronegative atom, so definitely it will not cause pairing and it will be high spin complex. Similarly, Cn here, carbon is donor atom, so when carbon is donor atom, then definitely pairing occurs and it forms low spin complex. In case of H2O, oxygen acts as donor atom and therefore, according to VBT, it should be high spin complex because no pairing. Similarly, FeCl6 minus 3, there is no pairing. In case of COH2O6 plus 3, again there is no pairing. Fine. So this one is clear. Now in next question, NiCl4 minus 2 is tetrahedral high spin, NiCN4 minus 2 is square planar low spin complex, but NiCO4 is tetrahedral dimagnetic. Explain the observation in VBT theory. Now see, we have already discussed these two examples, and there we have discussed that all the tetrahedral complexes are high spin, but in case of NiCO4, it came out to be a tetrahedral and dimagnetic complexes. So you have to find out the hybridization, and while finding the hybridization, or you will find that here the nickel has 3d8 4s2 configuration, and after pairing the 4s2 electrons comes to 3d8 and the configuration becomes 3d10, 4s0 and 4p0. So there is no choice for involvement of d orbitals in pair in hybridization, and therefore the only hybridization possible for NiCO4 is sp3 hybridization. So therefore this is we can say that exception that we have learned that all the tetrahedral complexes are high spin. Fine, because there is no availability of empty d orbital for dsp2 hybridization, therefore it forms sp3 hybridization. I hope you can draw the hybridization of it on your own. Fine. So now, one chemistry file special question. All those who have watched this video completely are chemistry files, that is chemistry lovers. And one chemistry file special question is that in a complex FeL6 plus 3, where L is neutral ligand, magnetic moment equal to 1.73 Bohr magneton. Find out whether it is inner orbital complex and or outer orbital complex. Well, I hope all the chemistry files can solve these questions. Try to solve it, comment in below, and I will definitely check it. Okay, if you have any doubt, you can ask me in comment box. So, in the next video, I will be discussing that there are various drawbacks of valence bond theories. Okay, it is not the final theory, and so in next video, I will be discussing about the drawbacks of valence bond theory. Till then, note down and solve this question and write its answer in comment box.